Welcome to your first lesson on PyTorch for deep learning and computer vision. As you might already be aware, PyTorch has been embraced by the deep learning world for its ability to conveniently define neural networks. Neural networks themselves can be fundamentally structured as tensors. And provided that PyTorch is built around tensors, there tends to be a significant boost in performance. Vaguely, a tensor is a generalization of matrices with n dimensions. It can be a zero-dimensional tensor, a scalar, a one-dimensional tensor, a vector. You can have two-dimensional tensor matrices, 3D tensors, so on and so forth. Before we begin our discussion on neural networks, let us first get familiar with the basic operations that can be done using tensors. Operations that we will apply throughout the entire course when training neural networks. We will be writing our code using Google Colab. Accessing Google Colab is very simple and intuitive. There is no setup required. It runs entirely on the cloud. To access it on your browser, search up Google Colab, and it should be the first link. Make sure you're signed into your Gmail. If you don't have a Gmail, you'll need to make one. And once you're logged in, simply create a new Python 3 notebook. And we will call this notebook Tensors Crash Course. This is quite similar to Jupyter Notebooks. We will eventually be using it for its free GPU, but notably, many packages come pre-installed for us when using Google Colab. Unfortunately, Torch isn't one of them, so in our first cell, we run the following installation. pip3 install torch. Alright, and as it's installing, inside of our first cell, we import torch, and on a new cell, once we've imported it, we will create a one-dimensional tensor using torch, torch.tensor. And this will contain a range of values from 1, 2, and 3. And we'll store this vector inside of a variable called v. And now, printing this value, v, results in our one-dimensional tensor output. One can also determine the data type contained within this tensor by simply looking up the D type. And it contains 64-bit integers. Simple enough. And now indexing a tensor is very similar to how you would index a Python list. To demonstrate this, we can access the 0th index of our tensor with the typical square brackets. Accessing the 0th index. And now we can index number 1, giving us the value 2. The second index 2 gives us the value 3. This is nothing new, very similar to how one would index Python lists. Note that there is a more efficient way of specifying a range for a tensor, but for simplicity we'll just keep it as such. And we will add 3 more elements for 5 and 6. And now we will slice from index 1 to index 4, 0, 1, 2, 3, 4. And notice it returns the integers at indices 1, 2, and 3. It does not grab the integer at index 4 since the stop index is exclusive, as you would have already seen in Python. If one wanted to grab everything from index 1 and beyond, you can simply use the same shortcut as what would be used for a Python list, which is simply the colon itself. And running the code, we get the expected output. Grabbing everything from index 1 and beyond. Alright, and now let us copy this line of code and rename the variable to f, as we will set it equal to a float tensor, torch.float tensor. The difference can be distinguished by printing the output, printf. And this results in a tensor of floats. If you print the data type, printf.dtype, our tensor clearly contains float type elements. Very intuitive. Determining the size of your tensor is determined by the size method. No tricks there. Clearly containing a size of 6 elements. Alright, on a new cell, our next goal will be to rearrange this tensor and have it adhere to new dimensions. Rather than having it be a single row of elements, we will view this tensor, v.view, to have 6 rows of data in a single column, v.view 6, 1. Outputting this result, our tensor is reshaped to have 6 rows in one column. If you come from a NumPy background, this is very similar to the reshape method that you would use to reshape arrays. And just like the reshape function, what you rearrange your tensor to must be compatible with your original input. i.e., if I were to rearrange my tensor into 7 rows in one column, it would throw an error, since I only have 6 elements, which would be insufficient to make 7 rows out of it. However, if I reshaped it to have 3 rows and 2 columns, outputting this result, our original input is rearranged into the expected configuration as 3 times 2 equates to 6. No tricks there. There will be many instances where we'll have to reshape, so it's good that we're familiar with it now. Alright, and now instead of placing 2, if I were to replace it with -1, this value will be inferred based on the length of the tensor, such that the length of our tensor is 6, with a constraint of 3 rows, so the number of columns must be 2 to ensure compatibility. And indeed, it did infer the correct number of columns. Whether you want to explicitly specify the number of columns or use -1 doesn't really matter. This just saves you the trouble of worrying about the size of your tensor. And finally, throughout the course, there will be many instances where we receive our data in the form of NumPy arrays, which we have to convert to tensors. To simulate this, we will start by importing import NumPy as the alias np, importing all the submodules and functions from NumPy, which can now be accessed through the alias itself. And now we will create a NumPy array a is equal to np.array, and it will contain the values 1, 2, 3, 4, and 5. If you're unfamiliar with NumPy arrays, they're very familiar to Python lists, the main distinction being that they're much more convenient for numerical operations. As we'll be mostly working with tensors, let us concern ourselves on how to convert these NumPy arrays to tensors. We can do so by setting a variable name, tensor cnv for tensor conversion is equal to torch.fromNumPy, the NumPy array a. Printing the converted tensor, printing tensor underscore cnv, as well as the tensor type, tensor cnv dot type. Clearly, it was successfully converted. One can convert this back to a NumPy array by setting NumPy cnv is equal to tensor, the converted tensor dot NumPy. I seem to have misspelled this, and what we'll do is actually print the array NumPy cnv, and it gives us back a NumPy array. You'll come to see why this is useful as we go along with the course. For now, just know that we can interchangeably switch between NumPy arrays and tensors. That is all we're going to cover for this tutorial. In the next video, we'll cover basic vectorized operations that can be done with tensors. I'll see you in there.